This video is brought to you by mywayteaching.com.
In this part, let us see one more simple example. That is example number 9. So the statement is 2-point charges Q1 and Q2 of magnitude 10 raised to minus 8 coulomb and minus 10 raised to minus 8 coulomb respectively are placed 0.1 meter apart. Calculate the electric fields at points A, B and C as shown in this particular figure. They have given two charges Q1 and Q2 of opposite signs. We have to calculate the electric fields at point A, at point B as well as at point C. This is the question. Okay. Now let us find solution for this problem. So this figure is the reference for finding the solution to this problem. Okay. The electric field vector E1A here at A, due to the positive charge Q1, it points towards the right and it has a magnitude which is equal to E1A is electric field at A due to charge Q1. So that is equal to 1 by, again the same formula, and the value of 1 by 4 pi epsilon is 9 into 10 raised to 9 Newton meter square per coulomb square, and Q1 is 10 raised to minus 8, isn't it? And the distance, as you can see, it is 0.05, half of 0.1. This gives the electric field vector at point A due to charge Q1, isn't it? Which is equal to 3.6 into 10 raised to 4 Newton per coulomb. So the electric field vector E2A, which means the electric field at point A due to charge Q2, to the negative charge Q2, it becomes towards the right, and again it will be having the same magnitude. So hence the magnitude of total electric field EA at point A, we can consider it as summation of E1A and E2A, isn't it? This is very simple, which will be twice of E1A since both are equal in magnitude. So it is 7.2 into 10 raised to 4 Newton per coulomb, and this EA is, as you can see, it is also directed towards the right, isn't it? So this is the first part of the question. Now coming to the next one, the electric field vector E1B at point B due to the charge Q1, isn't it? That is given by E1B. Again here 1 by 4 pi epsilon naught is equal to Q1, and the distance again here it is 0.05, and the value will be equal to 3.6 into 10 raised to 4 to calculate. And next, the electric field at point B due to charge Q2, that also we have to calculate. It is not same as that of Q1 because the distance is not same here. You are seeing, right? So here it is, the distance from Q1 it is 0.05, whereas distance from Q2 it is 0.05 plus 0.05 plus 0.05, that is 0.15. So E2A, E2B will be different from that of E1B. that will be equal to 4 into 10 raised to 3 Newton per Coulomb. And the magnitude of the total electric field at point B, if you calculate, it will be E1B minus E2B. Here E1B is towards left and E2B is towards right. So only this negative sign, which gives the resultant electric field at point B as 3.2 into 10 raised to 4 Newton per Coulomb, and this resultant field is directed towards the left, as you can see here. Now the next part, that is the electric field at point C due to charge Q1 and Q2. Here again both are at same distance, and E1C will be equal to E2C. Which will be equal to 9 into 10 raised to 3. And the direction in which these two vectors point are also given here in the figure, isn't it? So here we can write EC as E1 cos pi by 3 plus E2 cos pi by 3, which is equal to 9 into 10 raised to 3 Newton per Coulomb. And here EC, it points towards the right, as you can see in this particular figure, isn't it? So basically this is a problem where we can see the different the electric fields at different points in a system. So here we have considered 3 points, that is at point A, at point B and at point C. Again, we have found the electric fields at those points. Now let us study about electric field lines. So now we studied about electric field, and now it's time to study about electric field lines. See, this electric field line, it is a vector quantity and we can represent it as vector. See, let us try to represent electric field E due to a point charge pictorially. Let the point charge, we will assume that the point charge is placed at the origin, okay? And we'll draw vectors pointing along the direction of the electric field with their lengths proportional to the strength of the field at each point. Which means around the point charge there will be electric field, so we'll represent that electric field in terms of electric field lines, and that strength of electric field is represented by the length of the electric field line. Okay. Okay, then the magnitude of electric field at a point, it decreases inversely as the square of the distance of that point from the charge, and the vector gets shorter as one goes away from the origin, isn't it? And it always pointing radially outward. You can see that in this particular figure. So here each arrow, it indicates electric field. You can see here. And the force acting on a unit positive charge placed at the tail of the arrow. This is the unit positive charge. When we connect the arrows pointing in one direction, the resulting figure, it represents the field line. You can see these are all field lines, electric field lines. and the magnitude of the field is represented by the density of field lines. Okay, the more the field lines, stronger will be the electric field density. E is stronger near the charge. So the density of field lines is more near the charge, and the lines, as they go apart, even that electric field strength will decrease and even the field lines will go apart. Okay. So the relative density of lines in different regions is very important. See, we draw the figure on the plane of paper, that is in 2 dimensions, but we leave in 3 dimensions. So if one wishes to estimate the density of field lines, one has to consider the number of lines per unit cross-sectional area perpendicular to the lines. So as electric field, we all know that it decreases as the square of the distance from the point charge, and the area enclosing the charge increases as the square of the distance. The number of field lines crossing that area, it remains constant whatever may be the distance. So these field lines carry information about the direction of electric field at different points in space, isn't it? And the relative density of field lines at different points, that indicates the relative strength of electric field at those points. And the field lines crowd where the field is strong, and they are spaced apart where the field lines is very weak. And this figure also shows some set of field lines. Here we can imagine 2 equal and small elements of area placed at points R and at point S normal to the field lines. Here you can see here in this, at point R a small area, and at point S we have imagined 2 small area. And the number of field lines in our picture cutting the area elements is proportional to the magnitude of field at these points. These field lines, they represent the magnitude of the strength. And from this picture, one thing is clear, that the field at R is stronger than the field at S, because the number of lines are more dense in place of R compared to S, isn't it? So that density is nothing but the strength. So easily we can say that. So in order to understand this dependence of the field lines on the area, or rather the solid angle subtended by an area element, let us try to relate the area with the solid angle. See, let us recall how we define angle in 2 dimensions. Okay. Then we can understand this concept easily. See, let us say a small transverse line element like delta L. It is placed at a distance R from origin O. Then the angle subtended by delta L at O, we can write it as delta theta, which is equal to delta L by R. In 3 dimensions, if you consider the same thing, then the small perpendicular plane area delta S at a distance R, that can be written as delta sigma is equal to delta S by R2. So in a given solid angle, the number of radial field lines is same. For 2 points P1 and P2 at distances R1 and R2 from the charge, the element of area subtending the solid angle is given by R21 delta sigma at P1 we can say, and similarly R2 to delta sigma at point P2. The number of lines which cut these areas elements are same, which means the number of field lines cutting unit area element is, we can write it as unit area element. At point P1, and it is equal to n by R22 delta sigma at point P2. Okay. And this picture of field lines, it was invented by Faraday to develop an intuitive, non-mathematical way of visualizing electric fields around charged configurations. And Faraday, he called them lines of force. And okay, but this term is somewhat misleading, especially in case of magnetic fields. So its more appropriate term is field lines only, not lines of force. And electric field lines are just the way of pictorially mapping the electric field around a configuration of charges. So in general, this electric field line is a curve drawn in such a way that the tangent to it at each point is in the direction of the net field at that point. Okay, an arrow on the curve is obviously necessary to specify the direction of electric field from the two possible directions indicated by a tangent to the curve. So a field line is a space curve, that is a curve in 3 dimensions. Okay.